Welcome to this video. We'll try in this video to solve some examples on nodal and loop analyses. We'll try to show how some special cases work where we have independent current sources, independent voltage sources, or dependent sources, how we can handle that in our nodal and loop analysis equations. Okay, we first consider this circuit here. This circuit has independent current sources. We have one current source here. We have an independent voltage source here. We have a voltage dependent voltage source. So the voltage between this point and this point is always double the voltage between here and here. Okay, so this is a controlling voltage and this is the dependent source. We would like to find the current IL, the current flowing in the 1 kilo ohm resistor using loop analysis, and we would like to verify our answer using nodal analysis. Of course, loop analysis and the nodal analysis can be used to solve any question, and you should be able to verify your answers in using one technique or the other. Okay, so let's start. I will first use loop analysis. I will define 4 currents in these 4 loops. Okay, and then I will attempt to apply KVL in each loop in order to find 4 equations and 4 unknowns. So my choice for the currents were as follows. This is I1, this is I2, this is I3, this is I4. And now I will go around each loop and then I will apply KVL. I will go loop number 1 in the clockwise direction. And every time I see change from positive to negative, I will count as negative. Every time I see change from negative to positive, I will count it as positive. Okay? So what we can do here, we can simply go around this direction. So this will be minus 12 volts. I can take this drop here as negative positive. So I'm going to count this one as positive. And this is positive in the direction of I2. So I can write it as 2K I2 minus I1. Or I can take it actually the other polarity. I can take it this way. And then because I'm going in the clockwise direction, I will count it as negative, and it's gonna be 2K I1 minus I2 as I write it here. Both of them are the same. So you say it is plus 2K I2 minus I1, or it is minus 2K I1 minus I2, exactly the same quantity. You continue to go around the loop, okay, and you get this here positive, negative. This will give you minus 2Vx because I'm going in the clockwise direction. Every time you see a dependent parameter, you have to get rid of it from the equations and write it in terms of your controlling over your parameters, the variables you are solving for, or the quantities you are solving for. You are solving here for I4, and here Vx, you can see here that Vx is nothing but I4 multiplying by 1K, because this branch is only related to the 4th loop. Okay, Vx is 1K multiplying I4. So I have to go back here in this equation, which I got from loop number 1, get rid of Vx. And this is a rule of thumb. Every time you see a controlling parameter appearing in one of your equations, you have to get rid of it and express it in terms of the currents in loop analysis or in terms of the voltages in nodal analysis. So so you substitute here. So this will give you now minus 2K I4. Okay, so you have this equation. What I'm going to be doing, I will move all the currents to the right hand side and I will divide by 1K. So this becomes minus 12 milliampere. This is what you have here. The coefficients of I1 I have here 2I1. The coefficients of I2 will be minus 2I2. Remember, I multiplied, so this becomes positive, and then I moved it to the other side. This is why I changed the sign. There is no I3 here, so you must have 0 I3. And then I4 minus 2, you move it to the other side, becomes 2I4. Okay, so notice that I added 0 I3 to remind you that you are going to use this one to build a matrix, and the matrix, if you don't include a 0 for a missing coefficient, you may end up with the wrong matrix coefficients. So it's better to write your variables always in order, and if there is missing unknown, you give it 0 coefficient. Now we go to loop number 2. Loop number 2 is pretty straightforward. We're gonna sum the drops in the clockwise direction. We can take it clockwise or counterclockwise, doesn't really matter. I can take all the drops negative, positive, negative, positive, negative, positive. So in everything will be in the same direction as I2. And let's go in the counterclockwise, it doesn't matter. So this one here becomes 2k I2 minus I1, positive, negative, positive. So this one here becomes 1k I2 minus I4, and then I go around, and this is negative, positive. So we get here 2k, and this is multiplying only I2. So I went this time in the counterclockwise direction. If you go in the clockwise direction, you get exactly the same equation, but with a negative sign. So if I go in the counterclockwise, I obtain this expression here relating I1, I2, and I4. Remember, the current flowing here is I2 minus I4. And remember, the current flowing here in this direction is I2 minus I1. And remember, the current flowing here in this direction from bottom to top is simply I2. So I have only one equation between I1, I2, and I4, which is this equation here. I divide both sides by 1k, and then I collect the coefficients. So this becomes 2 plus 1 plus 2. This will give me 5 I2. I1, I have here minus 2 I1, still there. There is no I3, so I have 0 I3. I have here, okay, let's see here, I4. You have minus 1 I4 is equal to 0. So this is my second equation. Now we have to apply, in the next slide, we have to apply KVL to loop number 3 and loop number 4. Okay? So let's see how we're going to do that. We are going to do that. So in loop number 3, as you can see, you have between loop number 3 and loop number 4 this current source here. This current source ruins KVL in this loop and this loop. You can't write KVL here and you can't write KVL here. Why? Because I don't know what is the expression for the voltage across this current source. The voltage across this current source depends on the rest of the circuit. Okay, the circuit is what determines this drop here. So I can't really write it as some current multiplying resistance. There is nothing like this. So in order to do that, so because of this current source, we lost two equations. We can't write KVL here, we can't write KVL here. So we lost the two equations what to get for loop 3 and loop number 4. So I have to find an alternative way of writing two other equations. Let's see what are these two equations. First, this current source flows from left to right. I3 flows from left to right. I4 flows from right to left. So the current in this branch, which is common to both loop 3 and loop 4, this 2 milliampere is actually equal to I3 minus I4. So this gives you the third equation. I can get one more equation by combining these two loops to get a super loop. And then we apply KVL around this super loop, and then we solve the resultant system of equations. Okay? So I can take the drop this way, positive, negative, positive, negative, positive, negative, and this one as it is. So let's go in the clockwise direction. This one will give me 2Vx. This is fine. This is positive, negative, so this becomes negative. So this is negative 1k I4 minus I2. Why did I write I4 minus I2? Because I took my drop as positive, negative. So that the current, this drop is in the same direction as I4. Okay, so 2Vx minus 1k I4 minus I2. Let's continue the clockwise direction. I have this drop. This is positive, negative, so I have to be negative. So minus 1k multiplying I4, only I4 here. I have to continue here, positive, negative. This drop is 1k multiplying I3, and I will include it with a negative sign because it's moving positive, negative. So this is what I have here, minus 1k I3, minus 1k I4, and then the third current, and then 2Vx. What you have to do now, you have to get rid of Vx. Every time you see a controlling parameter like Vx appearing, you have to get rid of it. This is a controlling voltage. So we know that Vx, I have to express it in terms of my unknowns. These unknowns are I1, I2, I3, I4 in this case because we are doing loop analysis. So Vx is not that difficult to see. Vx is 1k multiplying I4. So this becomes 2k multiplying I4. But you have here 1k I4, 1k I4 with a negative sign. So these two will cancel with this one. So I4 will disappear from this equation, and you have only I2 minus I3 is equal to 0 if you divide by 1k. So this is our fourth equation. So I write all four equations in a matrix form, and then I can try to solve it. Of course, I could have simplified it earlier if I get rid of I3 and write it as I2 in all equations, I obtain a system of equations in I1, I2, and I4 only, which is going to be 3 by 3. So you can always make substitution and reduce the number of unknowns. Anyway, I kept it that way, and I used my calculator to solve it. And the solution is as shown in the next slide. So using my calculator, I got this answer: I1, I2, I3, I4 minus 4 milliampere, minus 2.5 milliampere, minus 2.5, minus 4.5. So all these currents actually flow in the opposite direction. They all have the right magnitude, but they all actually flowing in the opposite direction because of these negative signs. Okay, now this tells me that the current IL, which I'm looking for, which is the current in 1 kilo ohm resistor, which is the current I3, okay, which is the current I3, is simply equal to minus 2.5 milliampere. Okay, now let's verify our answer using nodal analysis. Nodal analysis means you pick one point as a ground, and then you try to solve for the other voltages relative to this point. So V1 is the voltage between here and ground, V2 is the voltage between here and ground, V3 is the voltage between here and ground, V4 is the voltage between here and ground. Okay, so what we have to do, and this by definition of nodal analysis, you have to apply KCL at every node. Let's start doing that. At this node, we can't apply KCL. Why? Because I have a voltage source connected to it. But luckily, this voltage source is directly connected to ground, and this is one of the cases I discussed in classes. If you have a voltage source connected to ground, you don't need to use supernode or anything like that, because this will give you directly an equation. This connection here tells me that V1 is equal to minus 12, because this source is keeping V1 lower than ground by 12 volts. Notice the polarity here. So I can immediately get an equation that V1 is minus 12. I don't need to solve now for V1, because I already know what is V1. So I don't need a KCL equation here. Okay, so this is fine. Now we move to node number 2. Node number 2, if you try to write KCL here, you can't. Why? I know the current flowing out here, current flowing out here, current flowing out here, but I don't know what's the current flowing in this voltage dependent voltage source. I have to find a way of finding it. Okay, well, I don't really need to write KCL here. Why? Because the voltage between this point and ground is equal to 2Vx. And I can eliminate Vx because Vx is equal to V4 minus V3. Remember, and I'm repeating this again, if you have a controlling parameter like Vs, you have to express it in terms of your unknowns. In loop analysis, these unknowns are loop currents. Here in nodal analysis, these unknowns are nodal voltages. So I have here Vx is equal to V4 minus V3. Okay, so V2 is equal to 2Vx, but Vx is V4 minus V3. So I have this equation. If I reorganize it, I get that V2 minus plus 2V3 minus 2V4 is equal to 0. Of course, I have to put them in order again. So this is my second equation. And remember, here we are now solving only for V2, V3, and V4. We already know what is V1. V1 is minus 12. So I wasn't able to apply KCL here, but because my voltage source was connected to ground, I was able to get an equation. Okay, so this is good. Now we move to node number 3 and node number 4. If you apply KCL here, you get V3 over 1K. I usually sum the currents flowing out. So the current flowing out, V3 over 1K, V3 minus V4 over 1K, and this one flowing out is minus 2 milliampere is equal to 0. Multiply both sides by 1K, so this minus 2 milliampere becomes minus 2 volts. Move it to the other side, becomes 2 volts. V3 and V3 will give you 2V3 minus V4 here. And there is no V2, so I include it with a 0 coefficient. Okay, so I now need one more equation. I have this equation I can solve for V2, V3, and V4. I have this equation between V2, V3, and V4. I need one more equation. I will get it by applying KCL at this node here. So at node number 4, maybe I can explain this slide. Node number 4 here, I can simply say this current plus this current plus this current is equal to 0. So if you do that, I can simply say V4 minus V1 over 2K plus V4 minus V2 over 1K plus V4 minus V3 over 1K is equal to 0. And what you have to do, we have to get rid of, actually you can keep it that way. You can write in terms of V2, V4, and V3. This is fine. But what you have to remember here is to get rid of V1. So once you write it, you have to get rid of V1 and write it as minus 12 because we already know what's V1. Okay, so the last equation, as I explained, it will simply sum this current plus this current plus this current. This one V4 minus V3 over 1K. This one is V4 minus V2 over 1K. This one is V4 minus V1 over 2K. Replace V1 by minus 12 volts. This will give you 12 over 2. It will give you, actually I didn't divide by 2 here. I multiplied both sides by 2K. So this becomes 12. You move it to the right hand side, becomes minus 12. Okay? And because I multiplied everything by 2K, the coefficients of V4 becomes 1 plus 2 plus 2. It will give me 5 V4. The coefficient of V2 becomes minus 2 V2 here. The coefficient of V3, this is minus 1, but you multiplied it by 2K. This becomes minus 2 here. So minus 2, and 5. So now you write the system of equations, all three equations for V2, V3, and V4, and then you solve for the voltages. Okay, we did that, and we put them in a matrix form. And remember, the right hand side will be voltages because you are summing and adding voltages, so these should be voltages. Okay, you can use substitution, Gauss elimination, method of determinants. I used my calculator for doing so, and I obtained that V2, V3, and V4 are minus 9, minus 2.5, and minus 7 volts. And the current flowing here in this branch is simply equal to V3 divided by 1K. V3 is minus 2.5 volts. So minus 2.5 volts divided by 1K, you get minus 2.5 milliampere, which is the same answer we got using loop analysis. So whether you're going to use loop analysis or nodal analysis, you should be able to get the same answer. Okay, let's try one more example. This example would like first to do it using nodal analysis and then apply loop analysis. We have here independent current sources 1 and 2. We have an independent voltage source 1, and we have voltage dependent voltage source. So the voltage here between this point and this point is double this voltage V naught. Okay, so this is our controlling variable here, and this one will always be double this one. And we would like to find first nodal analysis and loop analysis. Okay, let's start with nodal analysis. We have one node, second, third, fourth, and fifth. We're gonna use the lower one as our ground as we agreed. Now we have to apply KCL here, 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 and here in order to find our solution. Okay, so I labeled these nodes V1 relative to ground, V2 relative to ground, V3 relative to ground, V4 relative to ground. So node number 1, node number 2, node number 3, node number 4. Okay, let's apply KCL here. You can't apply KCL here. Why? Simply because you have this voltage controlled voltage source, but luckily it's connected to ground, so I can simply say that V1 is equal to 2 V naught, but V naught is nothing but V4. V4 is the voltage between here and ground, and V naught is the voltage between here and ground. Okay, so from the first equation, I don't really need to write KCL here. Why? Because already this source gave me an equation, because it's connected between node and ground. It tells me that the voltage here is double V naught, but V naught is V4. So V1 will have to always be double V4. Okay, so this is one equation relating V1, V2, V3, and V4. This one equation, V1 is equal to 2V4. Now, let's move to node number 2. Can we apply KCL here? No, we can't apply KCL here. Why? We have this voltage source connecting node number 2 and node number 3. Okay, so how do we find a way around that? So this source here ruined KCL at this point and at this node and at this node. So we lost two equations. We have to get two alternative equations. We can see here that the voltage V3 must be equal to V2 plus 12. Okay, if you go around and you write the polarity, this is positive, negative, this is positive, negative. If you apply KVL around this loop here, you will see that V3 is equal to V2 plus 12. So the source gave me already an equation. So this is a direct equation. We need one more equation. and this one more equation, you have now to use a super node. So every time you see a voltage source connected between two nodes, and these are two internal nodes, and one of them is not ground, then you have to apply a super node. So we're going to use this as our super node. We're going to sum the currents, all the currents flowing out from the super node to be equal to 0. Here we have 4 currents flowing out. One current, a second, a third, and a fourth. So this one here is V2 minus V1 over 1K. This one is V2 over 1K. This one here is minus 2 milliampere because I'm talking about currents flowing out, not flowing in. This one here is V3 minus V4 over 1K. So these are the 4 terms I have here. What remains? Multiply both sides by 1K. Okay, so this is what we did here. Okay, and then you start to organize your coefficients. So let's see here. I have V3, I have V4. Okay, what I did here as well, I replaced V2 every time I saw, actually let me see here. Every time I saw V2, I got rid of it as well. Okay, so so this V2 here can be written in terms of V3. Anyway, after I organized all the terms, I collected all the coefficients, I end up with this expression here between V3 and V4. Okay, so this one here will give me 2V2, this will give me minus V1, I have V3, I have V4, get rid of V2, write it as V3 minus 12, and reorganize, and you multiply both sides by 1K, you'll be able to show that you have only one equation between V3 and V4. Okay, so the last equation, so now these two nodes gave me two equations. The first one is that V3 is equal to V2 plus 12 volt. The second one is summing all the currents flowing out from the super node, and I got rid, as I said, I kept only V3 and V4 here. Okay, I kept V3 and V4 in this equation. I got rid of V2 because V2 and V3 are dependent on one another. So I can keep only one of them. I don't have to keep them both. Okay, so you have to keep this one in mind when you have this equation that V3 is equal to V2 plus 12. Then you can either keep V2 or V3, but you don't keep them both. Just simplify the analysis, and this is what I did here. I got rid of V2 and I wrote everything in terms of V3, and this is the equation I got. I divided here, I simplified the equations, and I multiplied by 1K and so on, and I collected all the coefficients. This is what I end up having here in this equation. Okay, node number 4 is a benign node because it's not connected to any voltage sources, so we can simply say the sum of all currents flowing out from node number 4 is equal to 0. I have one current flowing out here, a second current flowing out here, a third current flowing out here. Okay, so this one here is minus 4 milliampere. This one here is V4 minus V3 over 1K. This one here is V4 over 1K. So V4 over 1K plus V4 minus V3 over 1K minus 4 milliampere is equal to 0. Multiply both sides by 1K, collect the coefficients. This will give you 2V4, this will give you minus V3, and you end up with this expression here. So now we have equations relating the three voltages that we have, and we can solve for them. Okay, we have only 3, not really 4. Okay, because I already eliminated V2 and I wrote it in terms of V3 and V4. So to summarize, we have actually 3 equations. I just want to remind you of this. We have one equation relating V1 and V4. So this is V1 and V4. We have a second equation relating V3 and V4. And we have a third equation relating V3 and V4. So really my unknowns are V1. We have here in this case we have only three voltages to solve for, not 4 here. We managed to reduce the order of the equations. So if you put them in matrix form, this is what we have. I wrote in terms of V2, V3, and V4. You solve for only 3. I could have solved for V1 or V2 and so on. Anyway, so this is the system I kept: 3 equations, 3 unknowns, And the thing that matters me, that I care about more here, is the expression for V4, because V4 is V naught. V naught is my voltage, okay? And if you solve this system of equation, you obtain that V4 is equal to 12.667 volts. So this means that V naught is equal to this value. So in this solution, it has to be clear what I did. I got rid of V1. This is what I already did here. I thought I got, when I think about it, I thought I got rid of V2. No, but I kept actually V2 and V3 and V4, and I eliminated V1, because V1, as we agreed, is related, is to V naught, and V naught is V4, so V1 is double V4. So I kept only three equations between V2, V3, and V4. And remember, the first equation is V2 is equal, this one here is simply saying V2 minus V3 is equal to minus 12, okay? This is coming from this loop here, that V3 is equal to V2 plus 12, okay? V3 is equal to V2 plus 12. So I could write it in this matrix here. And then once you solve, you obtain this value here for V naught. Okay, so anyway, you can reduce the number, if you can even reduce the number of unknowns further. I could have used this equation here to eliminate V2, and then I could have solved the system of 2 by 2 only, actually this one here, for V3 and V4. You could have done that, but I kept it only for the three parameters. Anyway, we're solving three equations, three unknowns. I eliminated V1, I kept only V2, V3, and V4. This is what we did. Other people can do it in a different way. You can only maybe keep V1, V3, and V4, or you can eliminate V1 and V2 and keep V3 and V4. There are many ways of solving it, but they should all give you the same answer that I have here. Okay, so now let's proceed to verify our answer using loop analysis. Okay, in loop analysis, we're gonna give every loop its current. So I have a current I1, a current I2, a current I3, a current I4. Okay, and then we have to apply KVL around each loop. KVL is fine if you have voltage sources. If you have a current source, you may end up with a problem. So let's see. If you go around this apply KVL here, and I'm gonna take the polarity of the drops, positive, negative in the first loop, positive, negative in the first loop. Okay, so I have here 2V naught minus this drop is equal to 0. So this is 2V naught, and the drop here is minus 1K multiplying I1 minus I4. And you should understand why I used it as I1 minus I4. Okay, because I took the polarity as positive, negative. This means this is in the same direction as I1. This drop here is really 1K multiplying I1 minus I2. And I'm going to take it also with the negative sign, because I'm moving in the clockwise direction. When you write an equation like this one, you have to take into account that you have to get rid of your independent or this controlling parameter, this V naught. V naught here, I have to write it in terms now of my loop currents. It is nothing but 1K multiplying I3. So I'm going to replace here V naught by 1K multiplying I3. Okay? So if you do that, this becomes 2K multiplying I3. I can collect all the coefficients, and actually I'm going to move all the currents to the other side. So here the coefficients of I1 will be 1 plus 1, then you get 2I1. I moved everything to the other side, remember, so the sign changed. This is I2, this becomes minus I2. This one here is with 2K multiplying I3. I divided by 1K and I moved everything to the other side. This becomes minus 2I3. Okay, and the last thing that I can get rid of is I4, because from this loop you can see that I4 is equal to 4 milliampere. So this is 4 milliampere, minus will be positive. You move it to the other, you actually keep it here, you keep it in the left hand side, it's still 4 milliampere. So what I did, I kept this 4 milliampere on the left hand side, and I moved all the other currents to the right hand side. This is how I obtained this equation. So this gives me one equation. Good. Now we move to loop number 2. Can we apply KVL in loop number 2? No, we can't apply KVL number 2. Why? Because we have this current source. I don't know what is the voltage drop across this current source. Okay, So, and I can also apply KVL here. So loop number 2, loop number 3, we lost them. We cannot write KVL here, so we lost two equations. We have to find two alternative equations. The first one is that the current flowing here from bottom to top is I3 minus I2. So I3 minus I2 is equal to 2 milliampere. So this is the second equation you can use. Okay? And the third equation is to create a super loop by combining these two loops. So let's go around and summing the drops. Okay? So negative, positive. So this will give me here 1K I1 minus I2. Negative, positive, this will give me plus 12. You come to here. I'm going to take the polarity of this one. I can take it this way. Positive, negative. Okay? So I'm going in the clockwise direction. Okay? I'm going this way in this loop. Okay? This bigger loop. So this is negative here. Negative what? Negative 1K I3 minus I4, because this polarity assumes that the drop is in the direction of I3. So minus 1K I3 minus I4. The last equation, the last drop I get is this one here. I'm gonna take it positive, negative, okay? And because I'm moving in the clockwise direction, I will count it as negative. So minus 1K multiplying I3. This will give me one more equation. I can use this equation here. I can reorganize the terms and move the constant to the other side and so on. I'll get one equation relating I1, I2, and I3. Okay, so this is my other equation here. I get rid also, if you get rid of I4 and write it as 4 milliampere and move to the other side, this becomes not minus 12 but minus 16. So now we don't really need to write KVL for loop number 4. Why? Because this current source here is only in a branch that's related to loop number 4 only. So I know that the current in loop number 4, which is I4, is 4 milliampere. I don't need to write an equation for it because I need its value. I know its value already. I need only to solve for I1, I2, and I3, and this is what I have. I have already 3 equations for them. I reorganize these equations and I solve them. I got this value here, okay? And I got I3 12.667 milliampere. This means that the voltage drop, the output, is equal to this current I3 multiplying 1K. And this will give you 12.6667 volts, which is exactly the same answer we got earlier using nodal analysis. So whether you use loop analysis or nodal analysis, you get exactly the same answer for any problem.